Ever really truly thought about what a photo on your phone is? I mean, beyond just being a selfie or a vacation pic, what is a digital image really? We're going to get into that because, believe it or not, the answer is the key to how we see and understand our entire planet from space. We see these incredible satellite images of Earth all the time, right? They're breathtaking, they're packed with detail, but they are so much more than just pictures. They're actually incredibly rich data sets. So what is an image like this truly made of? Well, science gives us a beautifully simple place to start, a two-dimensional array of pixels. Now, that might sound a little technical, but I promise it's an idea you already get. Think of it like this. It's just a grid, a very, very smart grid. And that right there is our first big concept. To really understand a digital image, you have to stop seeing a picture and start seeing the world. You see, every single digital image, from a funny cat photo to a satellite view of the Amazon rainforest, is built from these tiny little squares called pixels. It's short for picture elements. Each one is the absolute smallest piece of the image. And here's the important part. Every single pixel knows two things. It knows its location in the grid, like, say, row 5, column 10, and it has an intensity value, which is really just a number that represents how bright it is. So when we organize all these pixels into a grid to represent the real world, we call it raster data. This whole grid-based system is absolutely perfect for mapping things that don't have hard edges, things that just flow and change across a landscape. Think about the temperature on a hot day or the elevation of a mountain range. And you can see exactly how this works right here. We start with a real-world shape, maybe a lake. A rough grid with big, chunky pixels gives us this blocky, low-res version. But as we make those pixels smaller and smaller, the grid gets finer, and that digital image starts looking more and more like the real thing. It's simple, really. More pixels means you get more detail. Okay, so we've got a grid of numbers. That's a great start. But for now, it's just a floating picture. To make it truly useful for understanding our world, we've got to give it an address. We need to pin those pixels to the planet. And that process has a name. It's called georeferencing. This is the absolutely crucial step that transforms simple digital image into a piece of geographic data. It's what tells the software, the geographic information systems, exactly where on the Earth's surface this grid of pixels belongs. Without it, it's just a picture. With it, it's a map. And what's really remarkable is how little information a computer needs to place millions of pixels perfectly. It just needs to know 4 things: the coordinate system we're using, the real-world location of just one starting pixel, how big each pixel is on the ground, and the total number of rows and columns. With just those 4 pieces of info, it can figure out the precise location of every other pixel in the whole image. It's incredibly efficient. Okay, so our image is a grid, and now it's pinned to the Earth, but the information that's stored in each one of those pixels goes way, way beyond what our own eyes can perceive. So now it's time to talk about seeing the invisible. Think about it. Your phone's camera has sensors that are built to copy the human eye. They detect red, green, and blue light, what we call RGB. But satellite sensors, they are on a whole other level. They can see parts of the light spectrum that are completely invisible to us. This is what we call multispectral imagery. So instead of just one layer of RGB pixels, a multispectral image is like a stack of layers. Each layer, or band, is a grid of pixels that's recorded a very specific slice of the electromagnetic spectrum. Some of those are visible, sure, but others aren't, like near-infrared. So why even bother capturing light we can't see? Well, because that's where some of the most valuable information is hiding. An RGB image shows us what a field of crops looks like, but an infrared band, that can show us how healthy those crops are by measuring their chlorophyll. It can tell the difference between water and dry land in a heartbeat, or tell us about soil moisture. It's basically a superpower for planetary science. So now we've got a georeferenced, multi-layered grid of pixels. This brings us to our final and maybe most important concept: how we actually measure the quality and the detail of these powerful images. See, when we talk about a regular camera, resolution usually just means how many pixels it has. But in the world of remote sensing, that word has a much richer, deeper meaning. It's not just one measurement, it's actually 4 completely distinct types of detail. This table lays them all out. You've got spatial, which is all about the fine details. You have spectral, which is about the different colors or bands it's capturing. Radiometric, which measures the shades within each color. And finally, temporal, which is all about time,
how often you can get a new picture of the same spot. And the key thing to get here is that these are often trade-offs. You can't always have the absolute best of all four at the same time.
Let's start with spatial resolution. This is the one we're probably most familiar with. It's just the size of one pixel on the ground. So a high-resolution satellite with 10-meter pixels lets you see individual buildings. But a low-resolution satellite with giant 500-meter pixels, well, it's less detailed, but it's perfect for monitoring things on a huge global scale, like weather patterns, where you're trading that fine detail for the bigger picture. Next up, let's look at radiometric resolution. This is all about the sensor's sensitivity to light. On the left, you're seeing a 2-bit image. Each pixel can only be one of 4 shades of gray. It looks pretty harsh and it's lacking a lot of detail. But look at the 8-bit image on the right. It can represent 256 different shades. And suddenly, all these subtle variations in roads, in fields, and water just pop out. Higher radiometric resolution means we see the world with so much more fidelity. So when you put all of these pieces together, the grid, the location, the invisible light, and these 4 dimensions of resolution, you get something that is so much more than a picture. What you get is a completely new worldview. Let's just quickly recap the journey of one of these images. It starts as this structured grid of data. Then it gets precisely located in space. It captures information from all across the light spectrum, and it's defined by all these different layers of resolution. And the result? It's one of the most powerful tools we have for measuring and understanding our changing planet.
And believe me, this isn't just academic stuff. This technology is what allows us to track a wildfire's movement with high temporal resolution. It lets us monitor deforestation using spectral bands that can tell the difference between healthy and cleared forests. It helps us assess crop health, plan cities, and so much more. Every single one of these applications depends on us understanding the digital image not as a picture, but as a rich, multidimensional measurement.
And that really brings us to a final thought. This technology gives us an unprecedented, unbelievable ability to monitor the health of our planet in incredible detail. So the real question it leaves us with is this. With this new power to see and understand so much, what are we now responsible for?